Hello, this is Brother Cromar from the Math Department at BYU, Idaho, and these videos I'll be covering Lesson 15, which is Inference for Several Means, ANOVA. And here's the outline for these videos. First, I'll be introducing to you what ANOVA is. Then I'll be discussing hypothesis testing, and then wrapping it up with checking requirements and descriptive statistics. Notice that there's not any confidence intervals that we'll be covering for Lesson 15. Okay, so let's review or Unit 2, where we dealt with one sample, two samples, and now we'll be dealing with 2+ samples. So if you remember, when we deal with one sample or one mean, we either have standard deviation known or unknown. And when we deal with two samples, we have paired data or matched pairs, or we have independent samples. But now when we deal with more than two samples, we gotta use some type of method, and therefore, voila, we have analysis of variance. Okay, now let's talk about analysis of variance. Analysis of variance compares sample means. Shouldn't it be analysis of means? But what analysis of variance does is it compares the variation between each of the sample means and the variation within each of the samples. So ANOVA tests whether several populations have the same means by comparing how far apart the sample means are with how much the variation is within each of the samples. So for instance, if we had, say for instance, if this were test scores, there's the lowest test scores and the highest test scores, and X represents men and O's represent women. You could see here that the variation between samples here is larger than the variation within samples, so the means appear to be different. Okay. Now if we have something here in example 2 where it looks like the end of a love letter from a missionary, it looks like here the variation between the samples is similar to the variation within samples, so the means appear to be similar. So this is more or less what analysis of variance does. It looks at the variation across between the means and then the variation within the groups. Okay. So now here's a brief summary of the characteristics of an F distribution. This is the first time you've seen this. You are used to seeing a normal distribution and a t distribution. Now we're going to deal with a new distribution, which is an F distribution. An F distribution is right skewed. Unlike what you've seen before, you typically see a bell-shaped distribution. The values of F are never negative. You notice here on the graph below, the lowest it can get is 0. And p-value for the ANOVA test is the area to the right tail. We never divide this area in the tail, so we just grab the information from the right tail to get the p-value. And here's an example of it here down on the bottom right. Okay, so an analysis of variance statistic for testing equality of several means has this form. So F is the variation among the sample means divided by the variations among the individuals in the same sample. This was not referred to in the textbook, but I feel like this is something that needs to be stressed, that that's what the F statistic does, the variation between sample means and the variation within the samples. However, similar to other test statistics like the z-score or something from the t-distribution, the t-statistic, as F gets further away from 0, the greater likelihood that the value becomes an unusual value or rare event, and I should include here relative to the null hypothesis. So here's an example of a ANOVA table, and so there's 3 or 4 basic things I want you to understand from this. First of all, this first row represents the variation among sample means, okay? And then the second row represents the variation among the individuals within the same sample. And so what happens with what ANOVA does, it takes what are called mean square errors, which is the ultimate measure of variation between groups and within groups, and it takes this number here divided by this number to get your F, or your test statistic, for ANOVA. Okay, and then the fourth, and this is the third item, this is the test statistic here, and then the last item is this represents the p-value, and we don't have to do anything with this number. It is what it is. It is the p-value. Okay, so now let's talk about hypothesis testing. So there's 6 steps. Let's review back in lesson 14 of independent samples. These 6 steps are similar to the 6 steps that we've dealt with previous problems, where we state the null and alternative hypotheses. And so this is how we state the null and independent samples, and this is how we state the alternative hypotheses, whether it's a two-sided test here or a one-sided test here. Steps 2 through 4 we calculate using software, computing a test statistic, degrees of freedom, and a p-value. And then the last 2 steps is we reject the null hypothesis if the p-value is less than alpha. If not, then we don't reject. And then we state our conclusions. These last 2 steps are the same 2 steps that we've seen before when we dealt with hypothesis testing. Okay, so now when we deal with ANOVA, now we have the same steps, but now they're slightly different here. For instance, how we state the null and alternative hypothesis, we more or less state it in English. For instance, the null hypothesis, we say that all the means are equal. That's the null hypothesis. And the alternative is one or more of the means differ than the others. That's the alternative. Okay. Steps 2 through 4, we compute a test statistic, which is an F. We determine the degrees of freedom, but this time the degrees of freedom are going to be two numbers. One degree of freedom for what's called the numerator and the other degree of freedom for the denominator. We compute the test statistic, and then we'll be asking you to mark the test statistic and p-value on a graph of a sampling distribution. But then the last two steps are the same steps as you've seen before. We decide whether to reject or not reject the null hypothesis by comparing the p-value to the level of significance. And then we state our conclusions. If we reject the null, we have sufficient evidence to say that, and then we state the alternative in English. Or if we don't reject, we have insufficient evidence, and then we state the alternative in English. Okay. So now what I'd like to do is I would like to I'll go through one example. Let's go through one example where this was found in the online textbook. So Emmons and McCullough investigated the effects of gratitude on people's perceptions of life in a whole, and they studied 192 graduates. People randomly assigned to one of three groups. So there was a gratitude group where they were to list 5 things each week that they were grateful for. Hassel's group, the volunteers in the group recorded 5 irritants that occurred to them the previous week. And then the events group, people that recorded just 5 things that occurred in the past week. And then you can review this here on the online textbook, but basically the scores were recorded in each of those, and we wanted to test to see here as they wanted to determine if expressing gratitude affected a person's view of life in general, and then all the 3 different groups were scored. So step 1 for this, and we use a level significance of 0.05. Step 1 is state the null and alternative hypothesis. The null is that all the means are equal. Okay. The alternative is one or more of the means, or the mean scores differ than the others. Okay. Now steps 2, 3, and 4, we get that from software. Now I have the output here from SPSS, but this is similar to Excel. But this is where we get the test statistic. The degrees of freedom, it's 2 and 189. This is for the numerator, and this is the denominator. And then our p-value is 0.019. Okay, or 0.019. And so how we sketch this distribution is that it's a right skewed distribution since it's an F distribution. And then we shade the p-value, and we label our test statistic. And remember, since we always deal with the right tail when we're dealing with an F test. And since our p-value is less than our level of significance of 0.05, we reject the null hypothesis. And so we have sufficient evidence to say that at least one of the mean happiness scores is different. Okay. So what I'd like to do is I'll stop the part 1 of the video, and I'll continue with another example, and then discuss descriptive statistics and checking requirements.